Whenever we want to build a forecasting model, we have to always ensure that we partition the data. We have to partition the data into training data and validation data. Validation data is also sometimes called as test data. So the model that we build would be based on training data, and we assess the quality or the performance or the accuracy of the model that we have built using validation data. There are a lot of rules available. For example, if I give you say 100 records of historical data, you might want to segregate this in this fashion, wherein you might say 80% of the data would be training data. I mean, I'm going to build forecasting model using 80% of the data, and the remaining 20% would be used to test the accuracy of the model. All right. Instead of 80%, 20%, you can also proceed and use your own logic. You can say, or in ExcelR tool that we're going to discuss about, in this, when we want to partition the data, by default it is 60 and 40%. And we're going to try to partition the data using ExcelR, and we're going to look at a lot of options pertaining to ExcelR. However, we'll not be covering 100% of ExcelR because there is a very good reading material available for 400 odd pages, which you can read and accrue some knowledge on ExcelR. You can also go with 70-30 rule, 50-50 rule, 40-30 rule, 40-60 rule, so on and so forth. It depends on the business context also. For example, in the Amtrak dataset that we are going to deal with, it has 159 observations. And if you want to forecast for the next 1 year, since this data is monthly data, you would consider 12 months, right? 12 data points would be considered for testing purpose because we want to forecast for the next 12 months. So if I were to forecast for the next year, then probably this year data would make more sense, right? Because it's very close in time. For example, if someone asks me on what will be the monthly ridership from Jan 2017 until December 2017. Since this is for 1 year, I'll consider 1 year as validation data to test the accuracy of the model. And if I were to test the accuracy of the model, I'll go back in time, the previous year data. This is how the data is, right? We have data from 1991, Jan 1991 until May 2004, and we have in total, I believe, 159 observations when it comes to Amtrak ridership data. And you have the ridership data on y-axis and you have the time on the x-axis. So this is a time plot. In this, we are dividing the complete data into training data and validation data. So you take 147 data points as training data set and 12 data points as validation data set. Why 12? Because we want to forecast for the next 1 year, so we are using 1 year data for validation or testing purpose. Once you build a model, and if you're convinced that the accuracy of the model is good, right, and if you want to use the model for the future purpose, what we tend to do is we now combine the training and test data or validation data and consider all the data points to build a model which will be used for the future purpose. And when you use all the data points, you would not be able to measure or gauge the accuracy of the model. Since you have already divided the data into 147 and 12, and since you have already validated the data, validated the prediction or forecasting model, now we combine these and we build a model including all the data points because we have already validated and it was fine, right? And the model that we build using all these data points would be used for future forecasting purpose, right? So whenever we deploy model by, we deploy the model by joining training plus validation data to forecast the future values. Okay. How do we choose the validation period? In this example that we have seen, we have taken 12 months as the validation data. How did we decide that? Based on forecast horizon, right? So we want to forecast for the next 1 year. That's our forecast horizon. Maybe if you want to include seasonality, probably you look into 1 year data or quarterly data maybe. You look into the length of the series data that you have, right? That is the length monthly, quarterly, weekly, based on that. And there are a lot of underlying conditions which affect the various series that we have. All right. Now, if you want rolling forward forecast, for example, if you think about stock market. In the stock market, you will not forecast once and stop. You have to forecast what will be the stock value for the next second, for the next microsecond, and you continue this process. That is a rolling forward forecast, as opposed to maybe forecasting what will be the GDP of a nation for the next 5 years maybe. Right. So in this way, we define upfront on what will be the forecast horizon. Will it be rolling forward or will it be a one-time forecast? And these are a few things that we need to decide upfront. Okay. Now, when it comes to partitioning the data, we can partition the data in this. Go to the data set and show you once. So this is the data set. All right. So you have month-on-month data from Jan 91, Feb, March, April, so on and so forth. And you have this data until March 2004. And at the same time, we have the ridership information in thousands, right? 1709, and you have the ridership information for all the months. Now, in order to show you various models that we are going to look at, I've just come up with log of ridership, and here I've taken a natural log. I'm not going to do a deep dive on what is natural log, etc., but let me give you a sense on what this log, what this log is all about. Let me write it here itself so that it might. How many a particular number do we multiply to get another number? That is what log is all about. For example, if you have 16, number 16, and if we want to know log 16 base 2, that means how many times would you multiply 2 to get 16? Log 16 base 2 should be equivalent to 4. How did you get 4? Because if you multiply 2 by 2 by 2 by 2, you would get 16 there, right? That is log base 2. In that way, say you have another number, you can take 100. So log base 10, if you take 100, how many times should 10 be multiplied? Twice, right? So the answer will be 2 here, kind of. On similar lines, you can have log, natural log, and ln, right? So that is what we have done here in this scenario. You can do a thorough analysis on what is the difference between natural log and the normal log. So if you see here, it is ln that I've used. This is the natural. Yeah, that is the reason why your log will always be in decimal format. We are coming up with another variable called t, which is time period. This is the first data point, first time period, second time period, third, fourth, so on and so forth. And how many time periods data do we have? We have data for 159 data points. And I've taken t square. I'm going to explain on why we are doing all these things, shortly. Because when we look at the different forecasting techniques, we need to understand on how to build those. Now, we have created dummy variables from D1 until D12. D1, D2, D3, so on and so forth. Since the first data point, these 12, D12 is for different months. So you have month 1, 2, 3, 4 until 12 months. Since the first data point here is Jan 91, you have a 1 there, right? And when it comes to Feb 91, you have a 1 here. When it comes to March, you have a 1 here. When you have April, you have 1 here. For the rest of the entries, you have a 0, right? This is how you create dummy variables or indicator variables, both mean the same. And this is the data set on which we will be working upon. Now, if I were to partition this data, all you need to do is once you install your Excel Miner, you need to go to this menu option, which is Excel Miner. And here you see that we have partition the data time series, and you have a normal partition in data mining, right? There is a difference. When you partition using time series, it is going to partition in a sequence. So the first few entries, for example, let me click on this and show you that. So maybe I want to select the data from A until B. You can otherwise, just simply click on this and select a range basically. So here, when it comes to the time variable is month. So let me select month. Yeah, month. And the ridership data is a variable that you want to partition. So let me select that. And also the time period is important here. So that's okay. You should also have had time period there, which you should have selected here. Nevertheless, you can specify multiple options. Do you want to partition based on percentage? 60%, 40% is by default. Or do you want to specify the number of records? You also am changing it. And now I can change. I would say that training data is 147, and the moment you do that, by default, the rest of the values would be a validation set. Click on OK. There we go. So if I click on training data, it has selected the first 147 entries. Yeah. The last 12 entries are not selected because those are your validation data. We have the validation data. So we have the training data and we have the validation data now. Now, I'll explain about linear regression. When we perform linear regression on time series data, how that is basically performed. Now, that's from the partition perspective. Now let us discuss about naive forecast, right? Which is nothing but last sample basically. If someone comes to me and asks me on what will be the sales for September 2016, I simply am going to check with the person on what was the sales for August 2016. If the person says sales for August 2016 was, $10,000, I would say, okay, for September 2016 also sales will be $10,000. Say I'm on the last day of August 2016. If someone asks me on what will be the forecast for, or what will be the sales for October 2016, once again the same thing. You'll check the last value that you have. Here it's $10,000, and you'll say that for October also it'll be the same value. That is all this model can do, right? It just looks at the last sample and it will help you forecast on what will be the value for the next time period. So you look at the current time period value and you say that would be the same for the next time period. Not just for 1 year or 1 month, for the immediate next month. You can do it for 2 months, 3 months, 4, 5, and you can keep on changing the K value. However, the sales of August month would remain same for September, October, November, December, so on and so on. And when you have seasonal series, we tweak it a little. For example, if you want to forecast on what will be the sales for say December 2016, then you'll ask the person on what was the sales, what was the sale value in December 2015, because December month seems to be having some kind of seasonality. Hence, in that sense, it's going to help. Say you have used some technique, some forecast technique, and you have come up with, and say you have built a model. Now you need to determine on which model is the best. As I have already discussed in the previous tutorials, we have a lot of forecasting techniques available, such as last sample technique, moving average, exponential smoothing, autoregressive moving average, ARIMA, so on and so forth. If you implement multiple techniques for forecasting purpose, and if you want to decide on which forecasting technique is the best, you tend to use an error value, error calculation. Error is the actual value minus forecasted value. That's the error. All right. If you have no error, if you have zero error, that means your model is very accurate. So if the model is adequate, this error will contain no information. It will be zero, absolutely. And when you get error, you should evaluate the error. and the error values that you get should resemble a white noise. It should be uncorrelated. It should be random. It should have zero mean, and it should have constant variance. These are the statements which hold true for any error value pertaining to not just forecasting, but pertaining to your regression techniques also. In simple terms, there should be no pattern. Okay, there should be absolutely no pattern, and that is what your forecasting is all about. Now, uh, this is fine, but think about this. Forecasting error is less the better, is, you know, how less is more better is all dependent on your business context. It depends on how much forecasting error tolerance is acceptable. And there was an incident of O-ring which was actually contributing, or which has actually contributed to space shuttle getting blown mid-air. I think this happened in I believe it is 1986. Let me check. So NASA space shuttle crash O-ring. Yeah, in on Jan 28, 1986, a space shuttle Challenger disaster occurred on this date, right? And it broke apart 73 seconds into its flight, leading to the deaths of its 7 crew members. And it included 5 NASA astronauts, 2 payload specialists. Now, they have attributed it to the O-ring seal, basically. So there will be something called as O-ring, which is going to attach, you know, the main body of this particular space shuttle and the other components. Yeah, I mean, I'm not very sure of the technicalities here. So in these kind of scenarios, even a small error is unacceptable, right? Even a small forecasting error is unacceptable. So in this scenario, your forecasting error tolerance is very less. But think about you running a food restaurant, you have idli, and you have decided that, you know, idli circumference should be so much. If it is slightly more or less, that's absolutely fine, right? You'll not be so concerned about it. So in this context, forecasting error tolerance is higher, right? So in this way, it depends on the business context in which we are trying to use. All right. Another thing is forecasting error. Should the errors always be normally distributed? It may or may not be, right? You might have errors which are positively skewed. You might have errors which are negatively skewed. But what kind of error distribution is more applicable for your industry, for your sector? That all depends on the business context. For example, think about you dealing with, think about these are all errors, and you're dealing with errors pertaining to insurance claims. And you have the errors which are distributed, right? And on the x-axis, you'll have high to low, right? Errors, of course, it'll be in that sequence only, high to low, right? Number 0, 1, 2, 3, 4, 5 in that way. Now, what do you think? Just give a thought for a moment and let me know on which kind of distribution would you prefer for errors pertaining to insurance. So we need to prefer positively or right skewed distribution. The reason being, if there are too many low insurance claim errors, that is fine. But when it comes to high insurance claims, high cost, then the errors should be less. This would be the most ideal scenario. Normal distribution might not be the ideal scenario given this context. If you're negatively skewed, then you'll go bankrupt because you're doing a lot of errors pertaining to high insurance claims. A normal distribution is something like you are just surviving. Let us understand more about the forecasting errors. In this forecasting errors, you have the actual and forecasted series basically. You see that light blue color, that's uh, based on naive forecast, and you have a dark blue color that's based on the normal ridership data, actual data. And there is a difference between the actual forecasted values and your there is a difference between the actual values and the forecasted values. And when you subtract those two, you'll get errors. So for each and every data point, you will have a forecasted value and an actual value. When you subtract that, you'll get an error. Now, how do you quantify that error? These are all the techniques to quantify the error, evaluating the predictive accuracy. You can go with mean error, mean absolute deviation, mean squared error, root mean square error, mean percentage error, mean absolute percentage error. So these are the various formulae that are available. Now let us understand each and every technique in detail, but even before that, let us look into how should the errors appear. Once you get the error values, you have to actually look at these plots. And all these plots should resemble white noise. Your error plot should resemble white noise, means there is nothing abnormal about the data. If you look at this time plot, over time, for all the data points, when you plot the error should be random. There should not be any pattern associated with the errors. Errors should not be increasing over a period of time. Errors should not be decreasing over a period of time. Errors should be random. Second is lagged plot. When you do a lag plot, once again, there has to be a random pattern. There should not be any specific pattern associated with it. And then you have ACF plot or autocorrelation function plot. Here, none of your errors should be significant. We don't want errors to be significant. We want the lags to be significant for forecasting, but not errors. And then we have histogram. When you look at this, the errors are following a normal distribution, which is a good sign basically. Let us understand each and every error measure that we have just seen briefly. Right? The first one that we're going to discuss is mean error. If the mean error is around 0, that means the forecasts are unbiased. There's absolutely no problem with your errors. That is what you can claim if the mean error is 0. And model is unbiased, meaning model is unbiased to overestimation or underestimation. So it's neither overestimating nor is it underestimating. It is estimating accurately, right on target, right? And there's a desired property of the model. So let us understand this. Say you have built a forecast model based on moving average. And also you have used, say, exponential smoothing technique for forecasting. You have used two models. And using moving average, you have forecasted that the value is 101, but the actual value is 100. So if you subtract forecasted minus actual value, you get 1. Once again, if you subtract forecasted value minus actual value, you get minus 1. Forecasted minus actual value, you get 1. Forecasted minus actual value, you get minus 1. And when you take a mean average, you just simply add all these and take the average of this. So if you sum it up, it'll be 0. 0 upon 4 will be 0. So the mean error is 0. Now if you look at the second model also, here we have used, say, exponential smoothing, and say here we are using moving average, right? When it comes to, or either way, the other way around also. And when you use exponential smoothing technique, say you have got a 110, and in reality the value was 100. So forecasted value minus actual value will give you error. In that way you have error for all these forecasted minus actual values. Now if you take the mean error, once again you need to sum up all these. 10 minus 10 plus 10 minus 10 would give you 0. 0 upon 4 would give you the average, which is 0. So here for moving average, where the magnitude of the error is less, you're getting mean average equal to 0. And for the second model, where the magnitude of the error is high, still you're getting a 0. So hitting a 0 for both moving average and exponential smoothing, right? Despite the magnitude of the error being different. This is a drawback of mean error. And this is the reason why we have mean absolute deviation and we have mean squared error, right? So mean error has a disadvantage that some amount and large amount of error may have the same effect as we have seen. And to overcome this problem, we may define two different forecast measures. One is mean absolute deviation, another is mean square error. And here is the data. So you have the actual values here, and here are the forecasted values, and you get error for model 1. When it comes to mean error, in both of these places you have a 0. But when it comes to mean absolute deviation, you take an absolute value of +1 would be 1 plus 1, minus 1 will become positive. Absolute value of this is 1, minus 1 will be 1. Now if I take an average, it will be 1 plus 1 plus 1 plus 1, which is 4, and 4 upon 4 is the average, which is 1. At the same time, when you try to calculate mean absolute deviation for the errors for model 2, and if you try to take modulus here, in all the places, you get 10. And if you want to take an average, it is summation of all these, which is 40 upon 4, and you get 10. That is mean absolute deviation. Then you have something called as mean square error. In mean square error, rather than taking absolute, you'll square each and every value. So minus 1 square will be 1, 1 square will be 1, minus 1 square will be 1. Once again, if you want to square errors and take average, so mean square error, square the error and take a mean. Mean absolute deviation, take the absolute value and then take the mean of that. So if you take the average, it will be 4 upon 4, which is 1. If you square all these values, the minus sign goes away and then you'll get all positive values. Once again, square error, mean square error. So you have to take average of these square errors. If you sum all of these, you'll get 400 upon 4, that is 100. This is how the problem that we have seen pertaining to mean error is getting fixed in these two instances. But there is again another problem associated with all of these three measures that we have just discussed. All of these three are not unit free. And all of these three are also not scale free. What does that mean? Just think of a case that one is forecasting sales figures. If you express the sales values in Indian rupee, say 70,000 is a forecasted value, but say the actual value happened to be 60,000 rupees. Now if you subtract these two, you'll get 10,000 rupees. That's the error. 10,000 is the error. If I convert these into dollars, probably this will be $1,000, and maybe this is maybe $800 or $850, whatever be. If I represent these values in US dollars, you get $1,000 in this. And when you look at the error, it's only $150. So there is such a huge difference. 10,000 rupees, 150 and 10,000, there is a huge difference. And this is a very awkward situation wherein you're getting errors based on the units that we use. And one more great disadvantage with mean square error is that it's going to square the unit. Say you have forecasted that the sales will be $10,000 or $1,000, but the actual value was say $800. So the error is $200. If you do a square of the error, you'd get dollar square. And dollar square doesn't make sense. So since units are getting squared, you take a square root of that, and if you simply take a square root, you'll get $200. So the units which got squared, you're getting back those units. So our MSE root mean square error does not have this disadvantage, but still it has a problem pertaining to your your measure being unit free and scale free, root mean square error also has that problem. It's not unit free and it's not scale free. So how do we deal with that? Okay. So how do we fix this problem? How do we fix a problem associated with all these three forecasting error values? We fix those using these two measures: mean percentage error, mean absolute percentage error. Both of these are unit-free measures because both of these are represented in percentage terms. And this is the formula for mean percentage error, ET by YT, error by the actual value. Mean absolute percentage error is given here. These are all the errors. So think about this. You have the YT values, you have the fitted or forecasted values. The residual will be forecasted value minus the actual value, and you can calculate mean absolute deviation, square error, so on and so forth. And say we have used the last sample technique here for forecasting. That is why it's the last sample. The last value is taken away and then you get the rest of the values here. Last sample. Say we are using a 3-point moving average to do the forecasting. What is 3-point moving average? Or what is 2-point moving average? In what context does this make sense? Let us understand that and then come back here. So let me explain about moving average now. Say you have the sales in dollar and you have this information for every month. Say for Jan month the sales was $1,000. For the month of Feb sales was $1,200. In the month of March sales was $800. In the month of April sales was say $600, so on and so forth. Say May month sales was $1,300. What do you mean by moving average? You can calculate moving average for say 2 months. What do you mean by 2 months moving average? I'm going to look at the average for the last 2 months and I'm going to look at what was the average sales. And for every 2 months we're going to look at the average sales. That is called as moving average. So not just looking at what's happening month on month, but looking at on an average what is happening for every 2 months. That's your moving average for 2 months.